Welcome. This is Mr. Perry, and we have our next PowerPoint presentation by Ms. Fondriska. It's titled Atoms, Elements, Periodic Table, and Chemical Stuff. A little bit about our world and the universe. A little bit about the universe and you. So far, science has learned that everything in the universe is made up of something called matter. Now, matter is anything that takes up space and has mass, and we can say mass is bulk. And mass is the amount of matter in an object. The smallest non-living unit of matter is called an atom. And an atom is the smallest non-living unit in the universe. And what are the atoms made of? Well, atoms are made of electrons, which hover around the atom's nucleus. They have no mass and have a negative charge. The symbol for electrons is a small e with a minus sign. It also has a nucleus that contains protons, which are positively charged particles that have mass, and the symbol for protons is P with a superscript of a plus sign. And it also has neutrons. Now, they are particles that have zero or no charge and have mass. And the symbol for neutrons is a small n with a superscript 0. Now, these charges are like permanently parts of the atom, sort of like when you see a magnet. It has a negative side and it has a positive side. These are permanent charges that stay on these particles. Well, some models of simple atoms, as you can see here, we have the electron, and around the outside of the nucleus, and that nucleus is that red and blue center that the atom has, and the electrons are circling it like planets going around the sun. We have a neutron, which is in the middle there, part of that nucleus. It's like a Tootsie Roll part that has that chocolatey center. That is the nucleus, and in there you have a neutron, which has zero charge, has no charge at all. And the nucleus also holds protons. And so the nucleus is made of protons, which have a positive charge, and neutrons, which have no charge. And the outside is electrons, which have a negative charge. Let's hear more.
It's hard to imagine just how tiny atoms are. One sheet of paper is roughly 500,000 atoms thick. Volume-wise, one atom is as small compared to an apple as that apple is to the entire Earth. So you might be surprised to learn that chemists can actually see atoms, not with their eyes, with incredibly precise tools. The idea of atoms stretches back to ancient Greece, when the philosopher Democritus declared that all matter is made of tiny particles. The philosopher Plato even decided, wrongly, that different substances had different shaped atoms, like pyramids or cubes. The first modern evidence for atoms appears in the early 1800s, when British chemist John Dalton discovered that chemicals always contain whole number ratios of atoms. That's why it's H2O and not H2.40 or H square root of 17O. The reason for these whole numbers, Dalton suggested, was because you can't have half of an atom or 0.2 atoms, only whole atoms. It's actually kind of hard to imagine chemistry today without Dalton's insight, but it was controversial during its day. Why? Because chemists couldn't see atoms. Many considered them like negative numbers, useful for calculating things, but not existing in the real world. Even Dmitri Mendeleev, father of the periodic table, refused to believe in atoms for many years. So why didn't chemists just look for atoms under microscopes? To see something under a microscope, the wavelength of light you're shining through the microscope can't be larger than whatever you're looking at. Unfortunately, visible light is thousands of times bigger than atoms. So chemists had to wait for light with short wavelengths, like X-rays. X-rays were discovered in the 1890s by German scientist Wilhelm Röntgen, who realized that photographs taken with X-rays allowed him to see through objects. Röntgen thought he'd gone insane when he saw this, but today we're all familiar with X-rays from trips to the dentist and doctor. Chemists don't use X-rays to see through things, however. Instead, they bounce X-rays off things like crystals, which are solids with layers of atoms. When X-rays hit an atom in the crystal, they bounce back. Others slip through and bounce off the second layer down, or the third layer, or deeper. After being reflected, these X-rays strike a detector screen, like the ball bouncing back in Pong. And based on the pattern of where they strike the wall, scientists can work backward and figure out the 3D arrangement of atoms in the crystal. This reflection and interaction of light rays is called diffraction. X-ray diffraction, sometimes called X-ray crystallography, has led to dozens of Nobel Prizes for chemists since the 1920s. It also led to one of the biggest discoveries in science history, the structure of DNA. James Watson and Francis Crick get credit nowadays, but they based their work on the work of Rosalind Franklin, a crystallographer in England. She began taking X-ray pictures of DNA in 1952, and Watson's glimpse of one picture, photograph 51, was a vital clue in determining that DNA was a double helix. This incident actually remains controversial today because Franklin never gave Watson permission to view photograph 51. If X-rays let chemists peer at the structure of atoms, scanning tunneling microscopes finally revealed the atoms themselves. Rather than bounce light off something, an STM runs a sharp needle over the surface. It's like chemical braille, except the tip never quite touches. As the tip moves along the surface, scientists can reconstruct the atomic landscape, making individual atoms visible at last in the early 1980s. Lo and behold, the atoms weren't Plato's cubes and pyramids, but spheres of different sizes. By 1989, a few scientists had even adapted STM technology to manipulate xenon atoms and spell out words. We'll let you guess what company they worked for. Also in 1989, the chemist Ahmed Zewail moved beyond looking at stationary atoms and developed tools to see atoms in action. Zewail wanted to study how atoms break bonds and swap partners during reactions. So he developed the world's fastest camera, which shoots pulses of laser light a few femtoseconds long, a few billionths of a microsecond. While Zewail's laser flashed like a strobe, his camera snapped pictures. Zewail then ran the pictures together like a slow-motion replay. Since then, femtochemistry has provided insight into everything from ozone depletion to the working of the human retina. Zewail won a Nobel Prize for his work in chemistry in 1999.
Atom, atomic mass, atomic number, and elements. Protons equal a positive charge, as we said before. Protons live in the nucleus of an atom, that's in the middle, and have mass. That means they take up space. A stable atom has an equal number of protons to its electrons. Remember that. If you have 5 protons, that means you have 5 electrons. If you have 10 protons, that means you have 10 electrons. Protons always equal the same number of electrons. And neutrons have a neutral or no charge. They live in the nucleus of an atom and have mass. So to find the number of neutrons in an atom, you have the number of neutrons equals the atomic mass minus the atomic number. Let's find out a little bit more about those two things, atomic mass and atomic number. The atomic mass of an atom equals the number of protons plus the number of neutrons. The atomic mass is usually a number with a decimal point. The units for atomic mass is AMU, or atomic mass units. And the atomic number of an atom is equal to the atom's number of protons, which, as we said before, is actually also the number of electrons. So if an atom has 5 protons, its atomic number is 5. Well, there you have it, ladies and gentlemen. We have a good start to our series on atoms. Have a lot of information to get started. Remember, protons positive, electrons negative, neutrons zero charge. Let's get going. Let's hit it and quit it. Let's go.